Okay, so I just wanted to make a short video to underline some topics um, which are sort of things I want to research more, things I want to learn about more, um, etc. Um, so the first ones are a few topics of um, sort of future research. One of them I just thought of this morning um, is something like a map of mathematics. Okay, um, you see, with category theory, we have these different areas of mathematics: topology, geometry, and so on. And with category theory, we can think of those basically as categories. Okay, so for example, the geometry of smooth shapes would be modeled by, say, the topos of smooth spaces. The So that would be like, differential geometry or something. Topology, perhaps we could model that by the topos of, I think it's the topos of closed Hausdorff, compact Hausdorff spaces. Um, and there's a topos of music, there's a topos of quantum, there's a quantum topos, there's a topos of sets, there's a topos of there's an effective topos which models computation, and so on. So we can think of these different sort of fields of mathematics as categories with various sort of added assumptions, axioms, if you like. Um, and so then it should be possible to visualize how they are related and which ones are more closely related. For example, if you've got two fields of mathematics and the axioms for them are very similar, maybe they have all the same axioms apart from one or something, maybe we could visualize them as being quite close to each other, and so on. So this is a sort of fuzzy idea at the moment, but maybe it should be fuzzy, at least to start with, because if one wants to just get a kind of feel for these things, maybe that one could start by just sort of saying, for example, something very rough like how many axioms do different fields vary by, and that would be like a measure of distance between those different fields of mathematics and so on. But I'm sure it could be made more precise. But one of the issues of this is it often depends how you look at things, right? Like, for example, if you view numbers as the kind of primitives of mathematics, then of course number theory is going to look quite central. In category theory, we find that ideas of natural number objects are quite far out, really, comparatively. Not all categories have natural number objects, and so on. So perhaps sets would be closer to the middle. But it's an interesting matter anyway. How can we make a map of mathematics? Okay. Another idea is the idea of infinitely rich objects and constructions using iterative union, intersection, and complement. So I had this idea that in some categories you can have this notion of kind of infinitely rich objects. So that would be like an object which, for any finite object, there's a sub-object of that one which is isomorphic. There's a sub-object of your infinitely rich object which is isomorphic to the finite object. And if you take that and then you take that infinite object, you can talk about its sub-objects, and you can do unions, intersections, and complements on those sub-objects. And if you have a natural number object, you can iterate on those. So you have some kind of a a kind of arena for doing computation. In some sense, it's more kind of general than computation, really. Something like kind of Tinkercad, but hyper general. And it talks about this a bit in one of my videos on natural number objects. Another idea is about the Stern-Brockott tree. So it seems to me that there's some issues about properly modeling the real numbers in Toposes. The Dedekind cut definition is that equivalent to the Cauchy sequence definition of reals. Depends on the Topos. But there's also this idea of modeling real numbers as path through the Stern-Brockott tree. And if you're dealing in the category of graphs, or perhaps the category of dynamical systems, you can model that quite directly. You can literally have a graph that represents the Stern-Brockott tree. And so that gives another kind of view of a continuum, which I think is interesting to explore. Another thing I want to understand better, I've done some research already on the category of functions. Okay, so set to the power of a non-trivial arrow. And it's a nice one because it's easy to understand in generality what the exponential objects are, sub-object classifier and so on. And I think it's a great arena for, because it's a non-classical topos, it's not Boolean. So I think it's a nice arena for understanding Mitchell-Benebaugh language and its applications and so on. Trying to talk about different things in there. I have some results about certain kinds of symmetries which occur in this category that are quite interesting. The main one being, like an arrow in this category, if you have a function f from a to b and a function f dash from a dash to b dash, then an arrow in the category from this first object to the second one is a pair of arrows, one which we can call G from A to B dash, and another one we can call G dash from B to B dash. But the thing I noticed is that when we have an arrow from one object to another, we can do a kind of flip. So then we can think of these as objects and the F and the F dash as arrows. So there's a very deep kind of symmetry there because of that. And of course, it can be generalized. So we can talk about this kind of thing when we have any category to the power of an arrow. I want to also be able to compute the exponential objects in dynamical systems. That's something I've wanted to do for a long time. And basically in this category of dynamical systems and also in the category of graphs, but I think that's been done quite a lot. But in this one, I don't know if it's feasible to do it in general. It seems like a interesting kind of problem that has a fair amount of structure to it. But if we can do that, then we hopefully gain a lot of insight into the nature of this category. What are questions? Okay, this is something I in one of my videos on knowledge representation and so on, I talked quite a bit about how we can use ontology logs to try and convert a real world language into category theory, basically. But, if you just sit and listen to people talking, very often questions come up. People ask questions. So how do we model a question? Is it in a categorical sense? Could it be like one of these exponential adjoints, something that's kind of waiting for evaluation or waiting for an input? For example, if you have an arrow from A times C to B, then that's going to have a transpose, which is going to be our F transpose from A to B to the power of C. But, you know, in order to evaluate this, we'd want to do an evaluation of F transpose times one C. Okay, so we'd need, like, if we're actually evaluating this, we'd need some kind of input from the C. So this is sort of waiting for an input in some sense. So is that a way we can think about what questions are? Another thing I was thinking about, there's this game, 20 questions, where you just ask yes or no questions. So that made me think about truth values. Like in that game, it's sort of Boolean, right? The answers to the questions are true or false. So you can think of those questions as kind of arrows into omega, the sub-object classifier. But then could you think about general questions in that context? If you had more truth values, like a truth value for every possible answer to a question, for example. Just a thought. We have this lambda notation in Mitchell-Benabal language. Can we formalize the idea of a Y combinator in that? Another thing, you know, when you learn a lot of category theory, you can get these kind of mental imagery, right? This kind of mental imagery, like your category of all categories, and you're zooming in to a particular category, like say the category of sets, and then you're raising that to the power of a pair of parallel arrows, and you're making the category of graphs, and you have your evaluator, and it's telling you about all the graphs and how they transform into each other. And then you pick a particular graph and you do something to it and you form an equalizer. And, you know, one gets a lot of nice mental imagery, but I think it would be worth kind of using some kind of procedural programming to make some nice videos of that kind of multiverse surfing that, you know, one imagines when thinking about stuff like that. There's also this, speaking of connection to computation, there's also this kind of Boole language, which is a language which people are developing for kind of like doing computations in a general topos. I'd be interested in integrating that with Mathematica and including sort of visualization of stuff to do with Presheaf, so you can actually see, you know, it's kind of like a combination of McClarty's work and Reyes' work, where, you know, you can actually see these computations on, say, the topos of graphs or the topos of functions or whatever, see the outputs, and also doing this kind of stuff with the category of smooth spaces. And then there's this project, which I've discussed before, about systematically converting English into ontology logs, which I think would be very useful for understanding about language. So there are a few different projects, not an exhaustive list, but a few things to have a look at. Other things, reading objectives this is just for myself. I want to finish reading McClarty, read some of Johnston, understand about the adjoint relations between different kind of functors related to topos logic, understand topology from a categorical viewpoint, closed Hausdorff spaces, groupoids and topology, understand more about this category of smooth spaces, the retraction theorem, understand about the effective topos, how that relates with recursion theory, how that relates with Cantor's diagonal argument and Chaitin's theory of algorithmic information, understand about computation in NKS from a categorical viewpoint. Something interesting in this, a particular topos is like the topos of dynamical systems, except every state has two arrows out of it of different colors. So a blue arrow coming out of it and a red arrow. So we can call this set. It's like set to the power of a monoid with a free monoid with two generators. Okay. So I think one can make NKS type systems where one starts with one of these things and does some fairly simple kinds of iterative transformations to get really complex dynamics going on and build up really complex objects like this. But one could do it so that the operations one was using were kind of easy to think about from a categorical viewpoint. Might give some interesting insights into the nature of complexity. I want to learn about the topos of music, the quantum topos, and also I think Reyes has a paper on topos and literature, or toposes and literature. So try to make more of this connection with everyday language. I wanted to understand more about Sheaves and Grothendieck approach to topos theory, relations between topos theory and topology, and understand more about ontology logs and the links to Reyes' paper and literary reference. Yeah, I've talked about that. Yeah.